Now we will consider the generation of SSB-SC signal. There are two types of methods available for the generation of SSB-SC. One is called the frequency discrimination method or filter method. Another is the phase discrimination method or the phase shift method. So these are the two methods available for the generation of SSB-SC. So let us try to understand frequency discrimination and phase discrimination method one by one. First, consider the frequency discrimination method. In this frequency discrimination method, the baseband signal is used to produce, using this product modulator, it is producing a DSB-SC signal. So first we have to generate a DSB-SC signal, xt cos omega ct. In DSB-SC signal, we have two sidebands. One of the sidebands must be suppressed by this bandpass filter, and this bandpass filter is actually allowing one sideband, and it will prevent the other sideband to go. So if we can suppress one sideband, what we will get is the SSB-SC. So this is a simple technique of generation of the SSB-SC signal using frequency discrimination method. Now let us try to understand the features of this particular method. Here the design of bandpass filter is quite critical, and thus puts some limitations on the modulating or baseband and the carrier frequencies. So if we count the limitations of this method is useful only if the baseband signal is restricted at its lower edge, due to which the USB and LSB are non-overlapping. That means the filter method is used for speech communication, where lowest spectral component is 70 Hz of the order of, and it may be taken as 300 Hz without affecting the intelligibility of the speech signal. However, the system is not useful for video communication, where the baseband signal starts from DC. That's a major drawback of this system. And another restriction of the frequency discrimination method is the baseband signal must be appropriately related to the carrier frequency. In fact, the design of the bandpass filter becomes difficult if the carrier frequency is quite higher than the bandwidth of the baseband signal. So this is another drawback of this frequency discrimination method. Now we will consider the phase shift method. The phase shift method uses this relation xt cos 2 pi fct plus minus xht sin 2 pi fct for the production of or generation of SSB-SC. So let us see how it works. The modulating signal is xt. So first we will consider this one. For that, xt must be multiplied with cos 2 pi fct. So we have a carrier oscillator that is generating cos 2 pi fct. So this product modulator will produce xtvc cos 2 pi fct, the first term. Next, we have to generate the second term. To generate the second term, first of all, we need this xht. How do we get this xht? Xht, or the Hilbert transform of xt, can be achieved by changing the phase of each component of xt exactly by 90 degree. So it is a special filter, Hilbert transform filter, that is used to change the phase of xt by 90 degree. So here we have xht. So once we get this xht, that must be multiplied with sine 2 pi fct. So to produce this sine 2 pi fct, this cos 2 pi fct is passed through a 90 degree phase shift. 90 degree phase shift. To produce this sine 2 pi fct, that sine 2 pi fct will be multiplied with xht to produce the DSB-SC signal xht vc sine 2 pi fct. Now we need an adder or subtractor depending on whether we want upper sideband or lower sideband, and the output is the SSB-SC signal. This is the phase shift method. Now we will try to understand the advantages of phase shift or phase discrimination method. So first of all, it can generate SSB at any frequency. So can generate SSB at any frequency. So we don't need any up converter. It can use the low audio frequencies as modulating signal. Low audio frequencies can be used as baseband. And third point, it is very easy to switch from one sideband to other just by changing from adder to subtractor. We can switch the upper sideband and lower sideband. So easy to switch upper sideband and lower sideband. So these are the advantages, but there are certain disadvantages as well. And one of the major disadvantage is the design of 90 degree phase shifter or the Hilbert transform filter. Design of Hilbert transform filter is very critical. Also, the second point, the network has to provide a correct phase shift of 90 degree at all the modulating frequencies, and that is practically difficult to achieve. So that is also main problem associated with this whole system is the Hilbert transform filter. So it is difficult to achieve exact 90-degree phase shift for all modulating frequency components. So these are the disadvantages of this phase discrimination method. Now we need to demodulate the SSB-SC. The requirements for SSB-SC receiver: first one is the high reliability. Second one is ability to suppress the adjacent signals. Ability to suppress adjacent signals, and obviously high signal to noise ratio, high SNR. Now in previous days class we have already seen that the double sideband suppressed carrier demodulation can be done with two methods. One is the synchronous detection technique, another is called the carrier reinsertion technique, which is almost identical to the synchronous detector, because the carrier, we have to generate the carrier locally, and that locally generated carrier must be well synchronized with the incoming carrier frequency. So the problems associated with synchronous detector is same as that of the problem associated with carrier reinsertion technique. The only thing is that in synchronous detection we have to multiply the incoming signal with locally generated carrier, but in carrier reinsertion technique we have to add them. So that's the only change. For SSB-SC we cannot demodulate incoherently, so SSB-SC must be recovered, original message signal must be recovered with a coherent technique. Coherent detection. So for coherent detection, product modulator will be used. We have oscillator, local oscillator, that will produce a frequency of FC. Then we must have a low pass filter. Its cutoff frequency is is almost equal to the maximum frequency component of the baseband signal. And finally we will get the output. So the SSB-SC signal can be written as, say, VC. Let us eliminate this VC. So simply xt cos omega ct plus minus xht sin omega ct. This is the SSB-SC signal. Now suppose signal at the output of product modulator is say S1t. So S1t is equal to St multiplied by cos of omega c t. This local oscillator is generating cos omega c t at frequency fc. Fc into 2 pi, it is equal to omega c. So S1t equal to St into cos omega ct. So if we multiply them, you will get xt cos omega ct multiplied by cos omega ct cos square omega ct plus minus xht cos omega ct sin omega ct. That can be written as xt by 2 1 plus cos 2 omega ct plus minus xht by 2 sin 2 omega c t. That is equal to half of xt plus half of xt cos 2 omega ct plus minus half of xht sin omega c t 2 omega c t. Now this low pass filter, the cutoff frequency is equal to FM hertz, where FM is the maximum frequency component of xt. So this term and this term, both the frequencies are of the order of twice omega c. So these two terms will be removed by the low pass filter. So output voltage V0t that is equal to half of xt. That means the output of this system is proportional to xt, so we can recover the original message signal. But here we have assumed that there is no phase and frequency error. We already gone through this phase and frequency error associated with the detection of DSB-SC signal. Now here also, in the similar way, we have phase and frequency error. That means if there is any change in phase of locally generated oscillator, or if there is any change in frequency of locally generated oscillator, then we will have the same effect of phase error and frequency error as that we have seen in the demodulation of DSB-SC signal. Now SSB-SC can also be, just like DSB-SC, can also be recovered with the help of carrier reinsertion technique, but we are not going to discuss that carrier reinsertion technique, because carrier reinsertion technique would have the identical problem of phase error and frequency error. That means we have to take care of this locally generated oscillator frequency, so that this local oscillator must be well synchronized with the SSB-SC signal, and that is the major point that we have to remember, that SSB-SC must be, frequency sensitivity of SSB-SC is extremely high. So if there is a smallest possible change in frequency or phase, the SSB-SC signal recovered SSB-SC signal recovered from SSB-SC would be distortion, full of distortion. That's the problem of SSB-SC. So let us now try to understand the relative merits and demerits of SSB-SC. First, the advantages. One of the basic advantage is the bandwidth. SSB-SC has got minimum bandwidth. Bandwidth is minimum. It has got least transmission power because it has to transmit just the one sideband, so power transmission is least power requirement compared to AM or DSB-SC. And third point is effect of noise. Effect of noise is less. So these are the advantages of SSB-SC, and there are certain disadvantages as well. The SSB system is very complicated. System, because both the transmitter and the receiver is very much difficult to design, and we have seen the transmitter section as well, that is difficult to design. Second disadvantage is very high frequency stability is required. Very high frequency stability is required for SSB-SC. So that is those are the problems of SSB-SC. SSB-SC as per application is concerned, it may be used in amateur radio, military application. Military application is one of the major application. Of SSB-SC. So we have already discussed the conventional AM, DSB-SC and SSB-SC, and we said that this DSB-SC and SSB-SC was actually some advancement in amplitude modulation scheme to recover it from some disadvantages of major disadvantages of AM. So DSB-SC, for DSB-SC the wastage of power was taken care of, and for SSB-SC wastage of power as well as the bandwidth was taken care of. But there are some problem associated with both the system that we have already discussed. Disadvantages we have already discussed. The major disadvantage of SSB-SC was the frequency stability, and because of this extremely high frequency stability, the cost of the SSB-SC receiver becomes very high. So if we want to use a broadcasting system, the receiver cost must be as small as possible. Now consider the situation of television transmission. Terrestrial television transmission, analog television, older days. So for this television transmission, if we consider that the bandwidth of video signal is of the order of say 5.5 megahertz, is the video bandwidth is of the order of 5.5 megahertz. If we assume, in that case, if we use AM, it requires a bandwidth of 2 into 5.5 megahertz, that is 11 megahertz. Similarly, if we use DSB-SC, we require the same bandwidth. What about SSB-SC? It requires 5.5 megahertz. So SSB-SC is the best choice, but for SSB-SC, the receiver cost is very high, so we cannot use this SSB-SC because the receiver cost will be very high. So we need a compromise, and that compromise is on the bandwidth and cost. To solve this problem, we have another type of modulation scheme called vestigial sideband VSB. So it is a compromise between DSB-SC and SSB-SC. So let us try to understand this VSB-SC in a briefly, because we are not going to discuss this VSB in details. This is a usual picture of spectrum of the baseband signal. Now if we use DSB-SC, the spectrum is this. This is the spectrum for DSB-SC, and you know the bandwidth is twice W, where W is the bandwidth of the low pass baseband signal. If we have SSB-SC, the corresponding spectrum will be like this. But if we want to make a compromise between this SSB-SC and DSB-SC, and the compromise is, for SSB-SC cost of the receiver is very high, for DSB-SC the bandwidth becomes very high. So what if we allow a portion of the other sideband, suppressed sideband of the SSB-SC? That means we are not allowing all the sidebands. We are allowing only just a portion of the other sideband. Portion means vestige. That is why it is called the vestigial sideband. So in this vestigial sideband, we will allow a small portion of the suppressed part of the sideband in this way. So one sideband will have a bandwidth of say W, and we will allow a small portion of the other sideband, so that some extra bandwidth we have to consider. So total bandwidth becomes slightly greater than W but less than twice W, right? So this is what we call the vestigial sideband. One sideband will be transmitted completely, and the other sideband, a portion of the other sideband, will be transmitted along with the along with the original sideband. And for that we have to use this type of system. Balanced modulator will produce a DSB-SC, and we will use a special low pass filter so that we will get a VSB. The special type of filter will be used to get this VSB. And we are not going to discuss about this deduction of this HF. This particular scheme was originally developed for the transmission of television. Now, to reduce the cost of the receiver for television, what is done? In general, VSB is suppressed carrier, but if we use suppressed carrier system, then the cost of the receiver would go high. So what we do in television transmission, we used to transmit a pilot carrier. Along with this original message signal, we will use a small pilot carrier, and that pilot carrier will not contain any information. But because of this presence of this pilot carrier, the receiver will derive its own locally generated carrier from that pilot carrier. So synchronization problem will be over. So this is how VSB-SC or VSB signal is used commercially for the television transmission. So we are at the end of, we have finished all the different type of amplitude modulation scheme. And we have also tried to understand the relative merits and demerits of different schemes.